Hello everyone, today we're going to be working on problem 3.17 and this problem is saying that the spring shown in figure 1, which is this figure right here, has a stiffness of 800 newtons over meters and a unstretched length of 200 meters, and it is asking us to determine the force in the cable BC when the spring is held in the position below and as well as cable BD. So, since we know that this is a spring problem, the first thing that should come in mind when we are working with a spring problem is that force is equal to the stiffness times delta, and that delta is equal to the final length of the spring minus the original length of the spring. So let's try to figure out that before we continue into the problem. So we are given the stiffness of the spring, but now we have to find the delta of the spring. So we know that the spring has a stiffness, and here it is. It says that it has a unstretched length of 200 millimeters. So that is the original length of the spring. So we can write that down. Length original is equal to 200 millimeters. And then if we were to take a look at the figure that was given to us, this figure already shows the spring stretched out. And as you could see, the spring is this spring right here, which it tells us that the length of that spring is 500 millimeters. So we know that the final length of the spring is equal to 500 millimeters. So now that we know the stiffness, the final length, and the original length of the spring, we could determine the force of that spring. So now we could write this out as that the force of the spring is equal to the stiffness, which is the 800 newtons over meters, times delta, which is the 500 millimeters minus the 200 millimeters. So that means that 800 times 300, but so then that gives us, like I said, 800 newtons over meters times 500 minus 200 is 300, but since our stiffness, we're working with meters, we're going to turn that 300 millimeters into meters. So if we convert that, we would get 0.3 meters. And we know that the meters would cancel out. So then that gives us that our force of the spring is 240 newtons. Now that we were able to find the force of the spring, the next thing that we're going to do is we're going to draw out a free body diagram of the figure that was given to us. So we're going to start off by drawing our x-axis right here. And then from there, we're going to draw a y-axis right here. So we're basically drawing the free body diagram around, or yes, with the center of joint B being like the center of that free body diagram. So we have our x-axis, then we will have our y-axis. From there, we're going to label it quickly. From there, we have to draw out forces. So we have the force of the cable right here, BC. We also have the force of the cable BD. And then we have the force of the spring AB. So from there, we're going to draw out the force of the cable BC. So we have the force of BC. Then we the cable BD. And from there we have the force of the spring, but we already know that that's 240 newtons. So from there, the next thing that we're going to take a look at is we're going to be using the the equilibrium equations. And something that I know that I'm going to be using is or that's going to be helpful is knowing the angles of these two angles right here. So to find the angles, what I'm going to do is we're going to go back up here. So I'm trying to find this angle. We'll call this these two. That angle theta, we'll call this angle phi. So to be able to find those angles, what we're going to do is we're going to take a look at these two angles and look at the triangles that are around them. So we're going to work first with theta. So taking a look at theta, we know that this side of the triangle is 400 millimeters long, and we know that this side of the triangle is also 400 millimeters long. So with correspondence to this angle, we know the opposite side of that angle and we know the adjacent side of that angle, which is why we could use the equation tangent theta is equal to opposite over adjacent. And then simply like that, we would solve for theta. So we know that the tangent inverse, that theta is equal to the tangent inverse of opposite over adjacent, which is the 400 millimeters over 400 millimeters. And that would give us that theta is equal to 45 degrees. So we know that that angle is 45 degrees. And now if we were to take a look at this angle and look at it like a triangle with, but this time instead of, yeah. So now looking at it from this way, once again, we know that the opposite side with this angle is 300 millimeters. We know that the adjacent side of the triangle, so the triangle's like this, is 400 millimeters. So we could use the same equation that we used before, but now remember our opposite side, instead of it being 400, is now 300 millimeters, and our adjacent side is also 400 millimeters. I just noticed that I wrote 40 instead of 400 millimeters. And if we were to input that into our calculator, we would get that B is equal to 36.87 degrees. So we're going to come here and we're going to write that out. That this angle is equal to 45 degrees. This angle is equal to 36.87 degrees. So now that we drew out our free body diagram and we solved for those angles that we're going to be using, now we're going to be working with our forces in the x direction to be able to find those forces in the cable BC and BD. So we have the sum of the forces in the x direction has to equal 0. So the first thing that we're going to take a look is at the 240 newtons that is acting because of the spring, the force of that spring. We could see that that is completely in a horizontal component. So there's just x component to it. There is no y component to it. So we don't have to do anything to that one. So we could simply put that as 240 newtons. But remember, we're working with our x component. So anything going to the left is negative. So that's going to be a negative 240 newtons. Now we're going to take a look at our BC. We could see that our force in cable BC is going to the right, so that's going to be a positive force. And from there, if we were looking at it as a triangle, we know that, let me write this out. So we're looking at it as a triangle. We know that this side is 400 millimeters long, and we know that this side is also 400 millimeters long. But for this scenario, we're just going to be using this side, but this side is also 400 millimeters long, and with correspondence to this side, with correspondence to this angle, this is the adjacent side of the angle, and we're trying to find the hypotenuse side. So the reason that we're using the adjacent side of the angle is because we're trying to find the x component to it. So it's not simply because we chose to work with this side, but because we're trying to find the x component of the triangle. And we're also, in the end, we're trying to find in the force in the cable BC. So that's our hypotenuse side. So once again, we're trying to find the adjacent side as well as the hypotenuse side. So adjacent over hypotenuse is cosine, which is why we're going to be using cosine. So we have our positive force of cable BC times cosine of 45 degrees. And then once again, if we take a look at our force BD and take a look at it like a triangle. Once again, we're trying to find the x component of that triangle, which is this side, which is once again the adjacent side of this angle. And we're again trying to find the force, which is also the hypotenuse side of that triangle. So once again, we could use cosine. And if you could see, force of BD is also going to the right, which is why it's also going to be positive. So we have that the force of BD times cosine of the 36.87 degrees, that is equal to 0. So then we have the negative 240 newtons plus, if we were to put cosine of 45 into a calculator, we get 0.707 times the force in cable BC plus cosine of 36.87 is 0.80 times the force of BD has to equal 0. From there, we could move over the 240 newtons to the other side. So that would be negative, sorry. No, that's positive, yeah. So this is the most that we could simplify this equation. So now that we simplified it to the most that we can, we're going to now work with our y components. So we know that the sum of our forces in the y direction also have to equal to 0. The 240 newtons, there's no vertical component to that, so we cannot include that in our y components. Now taking a look at our force BC, and once again looking at it like a triangle, now we're trying to we're trying to find this side of the triangle, since this is our y component of the triangle. And once again, we're still trying to find that hypotenuse side of the triangle. So this time we have the opposite side and the hypotenuse side, which is why we're going to be using sine, since sine is opposite over hypotenuse. And once again, looking at it for this triangle right here, once again, we're trying to find this y component of the triangle, which is the opposite side of this angle. And once again, we're still trying to find that hypotenuse side, which is why, once again, we could use sine for that force. But the difference is that force BC is going upwards, which is why that's going to be a positive force. Meanwhile, force BD is going downwards. That's why that one's going to be a negative force. So we're going to start off with the force of BC, which we said it's going to be positive since it's going slanted upward. And then we are going to times that by sine of 45. And now we have the negative force of BD times the sine of 36.87, which has to equal 0. So now that we have that, if we were to input sine of 45, we would once again get 0.707 times the force of BC minus, we have sine of 36.87, that give us 0.60 times the force of BD is equal to 0. So now that we also simplified that equation the most that we can, what we're going to do is I'm going to be using my calculator to solve these two systems. So if we were to write them next to each other, we would get 0.707 force of BC plus 0.80 force of BD has to equal 240 newtons, and then we have 0.707 force of BC minus 0.60 force of BD is equal to 0 newtons. So if you take a look at this, we could solve for the force of BC and BD by just using systems of equations. What I'm going to do to make things just a bit more quicker, I'm just going to be using my calculator to solve for force BC and force BD. The calculator that I use is the TI-36X Pro. It's very useful. So to put a system of equations into your calculator, at least on the TI-36X Pro, what you're going to do is you're going to turn on your calculator, you're going to press the second button, then you're going to press the button that says System Solver. So it should say SYS-SOLV. You're going to click on that, and you're going to pick the option where it says the 2x2 linear equations, and then you're simply going to input the 0.707. So you're going to take force of BC to represent your x, the force of BD to represent your y. So in the first equation, you're going to put 0.707x plus 0.80y equals the 240 newtons. Then for your next equation, you're going to put 0.707x minus 0.60y is equal to 0. And then you're going to press solve, and then it should solve for you. And you should get that the force in cable BC is equal to 145 newtons, and that the force in BD should come out to 171 newtons. And just like that, we were able to solve for the forces in cable BC and cable BD.